We have seen the words difference quotient before. Yes.
Gotta get back in front of them.
Yes. Last time I'll say it today. This is the end of 12th. Very important. Okay, limits from calculus. We have talked about the word difference quotient before. We've actually plugged into this before. But I want you guys to see the difference, not even the difference, sorry, the difference is literally a subtraction. The difference quotient is literally division. It's an important subtraction followed by division. Difference quotient. That's where the name kind of comes from. But even though we've worked with them before, the only thing that we've worked with before is how to find or how to plug in, given a certain function, like in letter A, given a function, how to plug into this part, what we call the difference quotient. The difference quotient is f of x plus h minus f of x all over h. All of this is review from chapter 1, somewhere where we were reviewing function notation. Somewhere where we were reviewing function notation. I'm going to take just a second because this is, I don't know, it's one of those things that just is hard for a lot of students. That math doesn't come super naturally to work with. So I'm going to review really quickly. You don't have to write this down. We're just showing where we've been before in function notation. Okay? Function notation, what am I referring to? F of x. Not f times x, f of x. So if I was to give you an f of x to be something like 3x squared minus 11, sure. Okay. That is our pattern, that is our formula, that is our, we should call it our function, okay? What changes when I ask you to do the following and find f of 3? Plug in 3 where x should be. I agree. But to that end, the pattern doesn't change. The setup doesn't change. What is happening to the input variable doesn't change. All that changes is the input. This is one of those things that our new curriculum teaches a little better than the old curriculum did. That x, yes, it's called an independent variable, but more importantly, it's called the input. It's what is put in function notation. So the input in letter A has changed to be what?
3.
So then what am I supposed to put in the input spot?
3.
So we put a 3 in there, and then the name of the game at that point is just to simplify using PEMDAS. Hopefully you guys know you would do the exponent first, and then you would do the multiplication second, PEMDAS, right? And then you would do the subtraction last. Do you guys agree? Can anybody help me out? How could this get harder? Instead of the 3, what's something that we could be putting in that would make it a little bit more difficult? Maybe a square root, maybe a fraction, maybe an x plus 3. Let's do a fraction next. What if I was to say f of x over 4? Okay. Question, does my formula change? Does the pattern change? Does the setup change?
No.
No. I have 3 times a quantity squared minus 11. I could have said that in the very beginning. Yes, we use the word x, but ultimately the x is just a common replacement for an input. So it's 3 times input squared minus 11. 3 times the unknown squared minus 11. Right? In letter A, the input was replaced with 3. In letter B, the input's being replaced by? Yeah, but the pattern is still the same. It's 3 times input squared minus 11. All that changes is now what's going to go into that input spot is no longer x, it's no longer 3. It has been substituted for what?
So 4.
Yeah, now the name of the game is substitute. So hopefully you guys know that you would do the exponent first. What do you guys got?
3x squared over 2.
Okay. X times x and 4 times 4. X over 4 times x over 4. The next thing that we would do is multiply.
3x squared over 16.
Yeah, I think there's like 3 over 1, so the 3 gets multiplied by the x squared. 1 times 16 is just 16. And then technically we could subtract, but let's just say they're not common denominators. One has x's, one doesn't. We'll just leave them separate. Is that okay? Now what would make it even just a little bit harder, let's go to what Nathan said. He said let's do f of x, make it a little more exciting, let's do x plus 5. Ready, set, you guys go. It's old school, it's old fashioned, but still tricky. Can you simplify it all the way? In Algebra 1, I would have done something silly in between these two, and I would have done f of cow with a little cow face, and we've been through cow squared minus 11. The point is, whatever is in the input goes into the equation. It doesn't matter what it is. And so in this case, what's my new input?
X plus 5.
So what needs to get put in to
X
my
plus
equation?
5.
But what's around the input? The same thing it always has. In this function at least. And how am I getting that every single time? It's all based on the function given. So we would go ahead and hopefully you plugged in x plus 5. Hopefully from PEMDAS, you know the very first thing to do is?
The foil.
The foiling. Good. Don't kill a puppy. X plus 5 times x plus 5. Long story short, you end up getting x squared plus 10x plus 25. Then hopefully from PEMDAS, you know the next thing to do is?
Multiply.
Good. Because we have a polynomial, we have to distribute. And the last thing is to subtract, to combine, in other words, to combine any like terms. 3 doesn't go into 65, so oh, so close. I just followed. Beware blindly following my lesson. Okay, so we can just go ahead and stop. I guess we could try to factor and stuff. If we had like a 0, we were trying to solve blah blah blah, but we're just trying to simplify. Function notation, f of x. Is it always f of x? No, it could be g of x, h of x, j of x. Probably not I, because that's usually an imaginary number, but there we go. Or like g. Let's come back here then. So when we read the difference quotient, we would say f, how do we say this parenthesis again? F of, and then whoever's inside, which is x plus h, minus f of just x all over h, right? Difference quotient, subtraction and division. Just think difference, subtraction, quotient, division. It's literally just telling us all the pieces. So then these steps, maybe they make a little bit of sense, because in order to find f of x plus h, we have to plug x plus h into the argument of x. So we could say into the, if I can get it, and that was really weird, we can get it into the input of the original function. We can get it into the input of the original function. Plug in, solve, solve, solve.
Yeah, so there's a circle.
Oh. So then like a big egg here, like that?
Yeah.
Okay, there you go. Oh, it's a nose, is that the smile? It's a weird little smiling face. Anyway, so, coming back. Let's see if we can solve the example. Let's start with letter A. Depending on how much room it takes, we might just go ahead and move on. Actually, we'll just go ahead and move on because we need to get to letter B. Otherwise, maybe it would take more time. Okay. So, for letter A, I want you guys to start where I said to start up above, which was, let's think about f of x plus h. He's the hardest part of this formula. Let's think of f of x plus h. Okay, so as we're thinking about the limit formula, I'll go back and get my red marker. There we go. I am trying to plug in, and when I plug in, I have the limit as h approaches 0. That doesn't change as I plug in. That's what's happening. H is h. It's just a variable. But I am trying to figure out what to plug into the f of x plus h spot and then the f of x spot. Now, who are we given right away? What's the easy one to plug in?
X. Yeah,
f of x. I know f of x, right? So I can say x squared minus 1, who f of x is, can go right into the f of x spot. True? So I can say f of x plus h minus x squared minus 1. So I can take f of x out, I can substitute in who f of x equals. The function can just go straight into that spot. I put parentheses because I'm subtracting the whole quantity, okay? But who am I still missing? F of x plus h. Because I have h, plug in 0, but guess what? It's going to be 0 over 0. Keep going. And we'll see that in a second. But first of all, I need to get the function notation out. That's just the pattern. I need to actually apply it to the specific function given to me in letter A. So when I go ahead and try to find f of x plus h, we can come off to the side if that helps. And think about what we were doing before. And say, I know the pattern of the function based on what they give me up above. Hopefully we can find or identify the new input, and where is he going to go?
in the X.
Yeah, where the old input was. The old input was x, and it was put into input squared minus 1. So if I take my input x plus h and say, okay, fine, it's his turn to be squared minus 1. What was happening to the x needs to also happen to the x plus h. So I need to put in the x plus h into the input spot. And putting parentheses, not because I needed parentheses originally, but I need parentheses now because I have a whole binomial, and I need the whole binomial to be squared. Now, just for sake of simplicity, I'm going to go ahead and say, okay, this is f of x plus h. So if that is f of x plus h, then where does that need to be plugged into, guys? Yeah. So we can take now that we have f of x plus h, and we can plug in. So now we can go ahead and say, so now we have the limit as h approaches 0 of x plus h quantity squared minus 1 minus x squared minus 1. Now some of you are like, wait a minute, well maybe not even. But I would say to simplify things a little bit, you could go ahead and distribute that negative right now. Instead of rewriting that, we could actually say, hey, let's simplify. So I'd have minus x squared, what would come next?
Minus plus 1.
Plus 1. A negative times a negative is a plus, right? All over h. Okay, now with that, kiddos, technically, whenever we have a limit, what's the very first thing we should try to do? Plug it in, plug it in. So if I plug in, I get x plus 0 squared minus 1 minus x squared plus 1 all over 0. I plug in h is 0, h y, because that's the variable, 0, 1, because that's what it's approaching. What does x plus 0 end up becoming? What do you guys notice about that numerator?
0.
X squared minus x squared. If I combine those two like terms, they cancel. Negative 1 plus 1. If I combine those two like terms, they cancel. 0 over 0.
Isn't that
For a difference quotient, when you try to plug in, you will always get 0. Because if you look back to the very beginning, if I take the old-fashioned difference quotient, if I put in what they're now writing a limit, just a heads up, the point of learning the difference quotient was to be able to now do the limit. Beginning of the year comes together with the end of the year. Kind of cool. But if I try to solve the limit, kiddos, what is f of x plus 0 minus f of x all over 0? Before I ever plug in for any function, the difference quotient is always going to be
can't exist?
0 over 0. And the difference quotient won't exist, but what will exist? The limit. The difference quotient at 0 when h is 0 won't exist, and that's the whole reason why we can't find the slope of the tangent line, because we can't have 2 points be a distance apart. You'll see that soon. But long story short, it's always kg. So for the difference quotient, we always have to keep going. So we can plug in, but we can technically do that from the beginning. So maybe we can just define the limit as h approaches 0, the difference quotient, always 0 over 0, always keep going. We go from the beginning. So how do we keep going with this guy?
Well,
Factor? Ooh. Radicals? No. Complex fractions? Sometimes it comes in old-fashioned ways. Oh, let's multiply stuff and combine like terms. Let's multiply stuff and combine like terms. So how am I going to multiply stuff? What do I have to multiply? This guy. How do I multiply x plus h times x plus h?
Foil.
Foil. Thank you. It's just like. I foiled quickly. X plus h times x plus h. You can think about, I did literally FOIL, and I knew that HX plus HX, the outer and the inner, were going to combine to 2HX. There's this old-fashioned, what is it, perfect square trinomial. You square the first, you square the last, and you double the outer, or you double the multiplication of the first times the last. So a plus b squared is a squared plus 2ab plus b squared. But long story short, can you just foil?
Yeah.
Does anybody notice anything that we can keep on going with?
Kill the x squared.
Hey, they die. What else?
Ones.
They die.
Take out an H.
Ooh, nice. We can factor out a common factor on top. And that is the proper math to do. We have to make sure that we can factor out before we reduce with a, oops, that's not h squared. Before we reduce with the denominator. But now that it's h times on top and h on bottom, what can we do?
H's.
Now pause. They don't cancel. They don't become zero. They reduce to one.
But this
Come on, Ricky.
So I can go ahead and I know in your head, I know. And I say cancel instead of reduce sometimes also. Trying to train myself to be better. Question: how do we finish this limit problem?
Oh, we plug in h.
Aha! That's exactly what we do. 2x plus, plug in h is 0, and you're left with 2x. That's weird. Yep. That's because in the very beginning we had not only h's, but we also had x's. So only the h's were getting substituted for, the x's were remaining.
What's the limit?
This is what we call this limit at the beginning. 2x is what we call the derivative function for f of x equals x squared minus 1. And if you guys have ever talked to a calculus kid, if they've ever talked about anything they're doing in calculus, the word derivative probably came up. Now, just so you guys know, the limit definition for a derivative, which we're going to talk about today in section 12.3, is the long way of doing a derivative. There are shortcut rules once you get the idea of who a derivative is and why on earth this limit of a difference quotient is necessary. Dun dun dun! 12.3. Why is this limit definition of a difference quotient, or should say the limit of a difference quotient, why is it important? What does it mean? Where does it come from? And when do we get to the shortcuts? Okay. We're going to start fairly basic. But the nice thing is, in the previous calculus at the beginning of the year, I told you guys there were two at the beginning of chapter 12. Did we talk about it? Talked about it in 10.2 with parabolas and quadratics.
We did intro the
Oh, we did. But at the beginning of chapter 12, when I talked about the tangent line problem, I said think skimming the graph. The tangent line skims the graph. Like in geometry, it skimmed a circle, and it hit at how many points in geometry for a circle?
1.
1. Now, what's a little weird in calculus? You still see the skimming, right, guys? You still see the skimming. Like if this was... If you think of ponds, if you think skipping rocks, and if you do it right, the rock hits and then keeps going, and that has like a parabolic trajectory, so that's a little different. But the idea is it skims at 1, right? Skimming the surface. Kind of the same thing here. Skimming the graph, it only hits once. It skims across the surface, only hitting at one point of tangency. What's weird about that speaker is on again. It didn't make noise when it wasn't doing anything.
It's always been on.
I like it.
Yeah.
You guys always hear the buzz?
Yeah, it feels comforting.
It's like white noise when you're sleeping. Now the rest of you guys are being annoyed. Okay, tomorrow, just Monday, I'll try to do that.
I'm an annoyance.
Another noise. It'll be
No,
more
some other people will be noise then.
I know. That was a joke. A self-aware joke.
Jokes are fine.
Ouch.
Blessed are those who come after themselves, for they will never cease to be.
He has a lot.
I do. I'm working close to him, I
Like
think.
that for college.
Wow,
I was
that's
like, yeah.
fantastic.
It's not always fun to laugh at yourself. But then if you can really do it. I was done. Move on.
Jason,
Okay.
no.
I don't even know. Stop. What are you doing?
I'm scared now. That's fine.
Skim. The weird thing in Precalc. The weird thing in Precalc is that we can have these funny functions that actually keep going. Guys, this is just a little weird because technically if this tangent line kept going, this one right here, if it kept going, where is it going to hit?
Oh no.
Oh no, it hits somewhere else. Okay, the point is not that it can't hit anywhere else. The point is, does it skim right around where it hits the point of tangency?
Yeah.
Yes. Does it hit somewhere else? Okay, whatever, but I don't know where it's going to hit. The point is, it's tangent right here at this, I don't know, this one's x3, y3, whatever. At this point, it skims, and in this local area, right around the point, it only hits how many times? Once. Okay? So even though since we're not just dealing with circles, and since we're not just in geometry anymore, even though curves can be funny, and even though lines can, I don't know, somewhere else hit a curve, the point isn't that it only can hit a curve once in its entire domain. It's for like a localized region. It literally skims at that point. Now, with those, I want to go ahead and talk about these tangent lines. An easy way to think about a tangent line is like with a pencil or with like the flat palm of your hand. And if you see a curve, you just think about skimming the surface. So if I skim the surface, and if my hand was like trying to be on the curve, which you can't perfectly be on, I mean, I guess I can try, but if I'm a line though, I can't mimic the curve, I can't bend, so instead I have to kind of just follow the curve. You see how my slope is getting lower? Okay, what sign slope do I have here? What kind of uphill or downhill do I have? Uphill, right? Because I'm going uphill. So I have a positive slope, but then the positive slope is getting lower and lower and lower and lower because it's getting less and less and less steep. So if I have a high positive number, and then if I'm going to a lower positive number, question, think about a number line. When I'm positives, I'm coming this direction. What am I going to pass through before going negative?
0.
Good. So I have positive, really positive slope, less positive, less, smaller number slopes, 0. And then what changes as I keep going? Now it goes negative, more negative, more negative, more negative. So on a number line, I'm on positive numbers, I hit 0, and I just keep traveling this way as far as the number values of my slopes. So, when I go down to these pictures below, help me out real fast. What would be the sign of the slope of the tangent line for graph, the first graph, which I could call graph A? For graph A, what's the sign of the slope?
Positive.
Good. So I could say that, let's just say slope n of the tangent line t, I could technically say like at p, but we'll just assume that p is the point of tangency, no big deal, is positive. True? So I have positive slope. How about for the next one? What would I say my slope of my tangent line is? Less than 0. Why? What kind of uphill, downhill motion do I have at that point? Downhill. Now, is it as steep as downhill up here? No. So it's not a super high downhill slope, which would actually be a really low negative number. But anyway, still, we're just trying to say, hey, it's negative. The slope is negative. And then in letter C, what would my slope of my tangent line be? I think if you're skiing on that, you're not going uphill or downhill. It's not that you don't exist, but you can do that. It's just boring. You're just going straight, you're going flat. Slope is 0. So for all of these, I could say my slopes of my graph are positive, negative, and 0. But question, what is my original function doing? The slopes are positive, negative, and 0, but what is my function doing? It's been a while since we talked about this.
I mean, as it reaches.
But how is my function moving at point P?
It's going.
It's
That
approaching
way.
positive infinity.
Yes, but there's an easier word. Remember the words that we use at the beginning of the year to talk about how a function moves if it's going in the upward position?
Increasing.
Ah, so we can say the function is increasing. What can we say for the second one? The function is
Decreasing.
decreasing.
Constant.
Nice. Constant. Now it's only constant at point P. It's decreasing for like all those points, and it's increasing for like all those points. But the point is, we're looking at the point P. There's a point way too much in that expression. But anyway, we're looking at point P specifically. And at point P, the function is increasing, which does correlate with the slope being positive. The function is decreasing, which correlates with the slope being negative. And the function is, which is a little bit weirder for you guys to think about, because if you were like a skateboarder on this, you'd be like, wait, I'm not constant, I'm moving. But in a way, you are constant for a moment before you change directions from decreasing to increasing. That's why in physics it talks about with vertical velocity, if the ball is going up in the air, positive velocity, before it starts coming down, there is a momentary stop in the sense of a place where the velocity is zero before the ball comes. Kind of interesting. Anyway, let's keep moving. So let me trace this graph so that they're all traced and then there's the point P. Okay. So we're looking at tangent lines. Why? Because the first big problem of calculus, or the first big problem that needed to be solved in order to apply to all these things they were trying to do, which is how calculus came about, is that tangent slopes are based on being at one point. We could call it point P, and we call that technically the point of tangency. But what's the dilemma for how we normally find slopes?
Is across the entire function?
You have to use 2 points.
If we're dealing with linear functions, yes, but across the entire function only works with lines, and we have way more functions out there. Lines have constant slopes, but everything besides lines, anything curved has varying slopes.
So you need to find the slope at an instant point.
Yeah, you have to have 2 points.
Can't express.
I need to have 2 points, and I can't express one slope for an entire function. Those are like two dilemmas that kind of go into one same category. The dilemma for me solving for slopes of the function is that I can't just do any 2 points on the function and have it be the slope for the whole thing unless it's a line. So that's a dilemma. And then the next part is, okay, well fine, if I can't just take any 2 points and find a constant slope like I did with lines when I have curves, then how do I do the slope? Okay, pick 2 points and no, I need the slope at 1 point. The dilemma is slope, by definition, needs 2 points. Because slope is linear, which is the dilemma when we're dealing with curves. Slope is linear, which is the dilemma when we deal with curves. Because curves, well, okay, that's where the tangent lines come from. It's like a linear component at a point on a curve. But slope needs 2 points, and that's how we did the old-fashioned m equals delta y over delta x, which equals y2 minus y1 all over x2 minus x1. We need 2 points. So how do we deal with trying to find a slope when we only know 1 point? And the rest of the points are like off in space. They're not even related to the function necessarily unless we have a parabola, and then we did a 10-2, and you guys didn't like that part of 10-2. We didn't even test on that part of 10-2. And that only worked for parabolas, and we have so many other functions out there. Well, let's say that there is one way that's very imprecise if you're doing it on your own. It can be somewhat accurate if you're given a picture. To try to resolve this dilemma, if you're given a picture of a function and a perfect tangent line at a point, I suppose you can eyeball it and say the slope kind of looks like. In this picture down below, approximating the slope visually, they give us the graph y equals x squared, f of x equals x squared. They give us a function, and they give us the point at which they want the tangent line, the slope of the tangent line, which is 1, 1. And they drew for us this line, because if we were to draw it, we might have it be a little bit off. We might kind of draw it and be like, it's kind of like that, or it's kind of like that, or it's kind of like that. You know what I mean? We don't draw lines so good. Maybe get a ruler out, but even then, it might be kind of hard to see, am I supposed to go that way, or am I supposed to go that way, or am I supposed to go that way? And those slopes are all a little bit different. So if they give us the slope, then we can go ahead and say, all right, cool. They're even nicer on this one. But if they give us the slope, then maybe we can go ahead and say, okay, I see this point, 1, 1. I wonder if there's another point I see.
2, 3.
You could go 2. You could see 3. And be like, it looks like it's approximately 2, 3. Is it perfectly? I don't know, maybe. So then we could go ahead and as we see that point 2, 3, we could do the old-fashioned y2 minus y1 over x2 minus x1. We could also just see the rise over run and say how far over. That's going to be 1. How far up? That's going to be 2. Long story short, our best approximation of this slope is going to be slope of the tangent line at 1, 1 of x squared. We'll say rise is 2, run is 1. Does this slope's sign, a positive slope, make sense with what you guys see? Okay, good. It's going up though. But the problem is, they gave us the picture, they gave us the line, and we kind of were like, hey, there's a nice-ish point, I'll use it. And to be honest, in this one, we're exactly right, because the point 2, 3 is on the line. The slope is 2, but there has to be a better way, because for us to actually have to graph a function, get out a ruler, try to skim it, and make it as perfect as possible, and then try to figure out another line that's kind of on the line, another point that's kind of on the line. We can't stop there. That's super imprecise. But the only kinds of points that we can find are the ones that have 2 points. And if we take any 2 points on a curve and try to connect, it's not going to be a curved shape. And it's not going to be a tangent line. And Cameron and JJ have been really gracious this time of things. So then as we go ahead and look at this graph, okay, what we can do is take 2 points. What we can do is connect those 2 points. What we can do is solve for the slope of those 2 points. But if you guys notice the slope of these 2 points, which is generalized right now, we have the slope of tangency, the point of tangency where we want the tangent line to be at. That line looks kind of like it's skimming, right? We want that line, but we can't find that line, not outright, not without learning a little bit more, which hopefully we'll do in this lesson. But we can choose some other point, and we're keeping it super arbitrary. So we have an x f of x, and then we go h away, so then maybe a quick thing to let you guys know, h is denoting delta x. It's just a nice little single letter for like a more complicated notation. We can go ahead and, without getting too deep, say x and then an x that's off by h, so x plus h, and then an f of x and an f of x that's, well, of x plus h. And if you guys think about our y2 minus y1 over x2 minus x1, that is how we get, and guess what, these are the same idea. Y2 would be f of x plus h, minus y1 would be f of x, all over x2 would be x plus h, minus x1 would be x. And if you guys think about how that simplifies, what happens to the x's in the bottom? Cancel. And we end up with, what's the name of this guy again?
Same as we did last time.
Otherwise known as the difference quotient. The difference quotient is just a snazzy generalized term for slope. And we kind of saw this in a preview to calculus. But when we say slope, we need to say, thank you, ma'am, slope of a secant line. This is slope of a tangent. This is slope of the secant. There are 2 points being used. Now, when we use 2 points on a line, we're golden because the line only has one slope. Any 2 points will do. If we have something curved, we're thinking about the curve as a line, and that's not always exactly ideal. So all this leads us up to what you see down here below. MSEC would be the slope of the secant line. Is the change in y over the change in x is the difference quotient. But kiddos, in the example that we just did at the end of 12.2, we didn't just find the difference quotient. Do you remember what was written before the difference quotient? And we were using the new stuff we've been learning in 12.1 and 12.2. Well, I did call it the derivative function, but what was new in our last example? What was written in front of the f of x plus h minus f of x over h?
Oh, there's a limit.
There's a limit. Well, why would we be taking a limit of a secant line slope? Why are we taking a limit of the difference quotient? Now, you don't have to write this. You don't have to write this. But the reason that we would be taking the limit of the difference quotient is because as the second point is away from the first point by a distance h, as that h gets smaller, what happens to the second point? It gets closer. And as h gets smaller, the second point gets closer. That's the tangent line. Let me give you a better illustration because this one's not bad. It's just not near as great as this one. Let's go this side. Do you guys see the tangent line? The one that skims the graph at one point? This is what we want to find. This is what we can't find. This is what we could find with the difference quotient. If we had like specific numbers to plug in. What's going to happen as I move, as I scroll along this taskbar? What's going on to point P? It's getting closer. Do you guys see how the slope is changing? This is all an algorithm. To do it by hand would have taken forever and been super annoying and yeah. But look at the algorithm. It's doing it all for us. And as we keep on scrolling, as P gets closer, do you guys see what the line is doing, the secant lines? What's it doing? It's getting closer to the tangent line. And can you guys look at the slope? Does the slope seem to be approaching anything?
0. -1.
Approaching.
You guys notice now I'm past it. So what's it approaching?
-1.
Yeah, if I come from both sides, it's approaching -1. I could have actually solved at -1. Not without what we would call a derivative. Not without this idea of the limit. Because if we were to solve at this one point, if we did y1 minus y1 over x1 minus x1, isn't that 0 over 0? Oh, it doesn't exist. No, wait, 0 over 0 means
Keep going.
calculus makes things impossible. So, to find the slopes of any graph, which I'm going to kind of like combine a couple pages in this one. The book decides to, I don't know, like say the same thing kind of over and over and over again. They're trying to introduce you guys to new terms slowly. I'm saying the slope of any graph, aka the slope of the tangent lines to a graph. The slopes of any graph, aka the slopes of the tangent lines to a graph, are the same thing as the slopes of the secant lines, which are great and all, but how does that actually play out? The limit of the difference quotient. The limit of the difference quotient. And I'm going to take this one step further and say, hey, this is the same thing as.
He heard himself.
The same thing as. It's not so much like the wording is the same because they can be used in different applications. But the slope of the tangent line can also be known as, or can also solve for, instantaneous rates. That's another way of putting it. Instantaneous rates of change, not average anymore. Rate equals distance over time. That's true, but then you have to have a change in distance and a change in time. That's average rate. Instantaneous rate, aka rate at one point, rate at an instant of time, not over 2 instants of time. And the more important wording, you say it's the derivative function of f of x. And the derivative function of f of x has a special notation. And a special notation of the derivative function of x is f prime of x, which is also known as f apostrophe of x. But don't you dare say f apostrophe, f prime. F prime is what we know. And this, kiddos, is actually one of the first named calculus forever cards. But how is it done? Wait a minute, didn't we solve this at the end of 12.2? Didn't we plug in to f of x plus h minus f of x all over h and didn't take a limit and get an answer. Now we are going to have to peek at a couple more things in 12.3 on Monday. However, even though technically I have this whole other page, my question to you is, wait a minute, do we actually need any of this? Don't we already have this formula written down? I have the formula written down. What's a little new in this one is that we're saying, hey, you could also have a c, like an actual number put into this, instead of just an x. What would change is that you're finding the derivative at a specific point. So you're plugging in c to the beginning before you do all the solving, instead of maybe finding the general and then plugging in c later. There are two different ways of doing it. They basically solve for the same thing, slope of anything. And then technically, guys, look, our book is a little funny because then they say, hey, now let's talk about slopes of tangent lines, instantaneous rates, aka derivatives. Okay, we don't need to write all that. So all we're going to do on Monday, because I've already kind of defined it all on one page, is we're going to say, hey, whatever wording we use, let's see if we can use our formula. Kiddos, technically, you know the math for 12.3. I would say you should get into 12.3 homework if you want to do corrections instead. That's not a bad idea. That's what it's good. Happy Friday.
Misty, is that?
There's a page.
Yeah, that's not mine.
Yeah, I know.
Okay, so that's the wrong way.
No, it's yours.
Healing.
You.
Lauren needs to read them.
Misty, is that big disgusting formula the same as like
The limit.
Whatever it was.
It's the definition of the derivative is how the calculus gets it.
So let's do it.
it's just a long way of doing the rules that Jason was teaching me?
Yes. 84%.
And each of the rules that you saw Jason doing are built upon came from that idea. The smart people
But
figure out how
someone
to
just
shorten it.
spent 15 years doing all the math and realized there
There you
was a
go.
short way.
Something like that.
Feel bad for that.